Okay, what I'd like to do today is continue with Chapter 8. So we'll quickly review what we've done. I've added some materials that I'm going to briefly talk about today, but particularly on nonparametric statistics, but there's some differences between what the book does and what the R code does. They're not actually different, it just appears to be different. So first of all, I'll bring up the, hopefully a window with, oh, I'm sorry, I already have it open. So this is a file, and I'm going to need to update it, including, in one case, I read an external file, which I don't think you have, and therefore you would have to enter it by hand. So I'm going to correct those aspects of it, and I'll update what's on the website. But let me first of all get the correct file. So let me bring Chapter 8. And I do have the .rmd file for Chapter 8. So now let me set the directory. Let's see. I'm not sure that's really set. That's maybe old. So let me reset it. Okay. So last time we talked about the one sample t-test and the two sample t-test. And let me just briefly review. So to start this out, I'm going to knit the whole document. And then we'll go back through and take a look at what we did. Let me mention, don't view these notes as complete. You need to look at the book. There's additional materials in the book. I plan to bring in some of that material into these notes. So for example, the histogram, I can superimpose a curve to it. And the various other things I'll do to enhance it. But first of all, in this case, we had the example of determining when runners hit the wall, which is hypothesized to be about 17 miles in a marathon. And so I showed you how to compute by hand. You can compute various quantities like the mean and the standard deviation. Notice that I have S as the square root of the variance of miles, but there's also a function, just SD, for standard deviation that gets it more directly. But this points out that that in fact is what the standard deviation is. It's the square root of the variance, the positive square root of the variance. And there is the histogram. Like I said, I'll probably enhance that a little bit. If you look at that, one of the assumptions is normality. The main other assumption is you have independent drills. That is, when you sample, the samples are independent of one another. Usually the independence you know by how the sampling was done. But if you look at that histogram, it's not completely clear whether or not that that histogram could, in fact, reasonably represent a normal distribution. It appears to be slightly skewed to the left. The problem is that we have a small sample size. We only have 12 runners, and histograms are notoriously unstable. So if I actually would take a normal distribution and I sample 12 and look at the histogram, I do that again, you would see, even if you use the same bins or the same widths along the bottom in terms of, in this case it's 15, 15.5 and so forth, even if I use those same intervals, you would see that the histograms could vary quite a bit from sample to sample, particularly when there's a small sample size. In terms of assessing normality, a better thing to do is to look at the normal probability plot, where you're plotting the sample quantiles against the theoretical quantiles of the normal distribution. In fact, you're actually doing it against the standard normal distribution, which has a mean of 0 and a variance of 1. The key thing to remember here, and I could, actually I'm going to change that plot so it looks like the one that I put in the book, but I'm going to change it perhaps a little bit and sort of flip the axes and draw a straight line through it. Now, as you can see, there's a little bit of curvature, but not a lot. And so normality may be reasonable here. Now, the other thing we looked at is, two things we want to do in terms of statistical inference. Anyway, if we're interested in a hypothesis that mu equals 17, say against the two-sided alternative that it's not 17, then we could test that hypothesis directly and either specify a significance level and make some decision, or we could simply compute a p-value and based on the p-value make a decision. The other thing we can do is construct a confidence interval about mu. And then the question would be, does the confidence interval contain 17? If the confidence interval contains the hypothesized value, then you're going to fail to reject the null hypothesis. So in order to get the confidence interval, and again, I'm viewing this as a review, both now of the last lecture, but also this is something that you should have had in an elementary stat course. And so to compute the confidence interval, you simply take the mean plus or minus the t quantile, or the t-value, times the standard error of the mean, or technically the estimated standard error of the mean, which is s over the square root of n. So the computations here, if we're doing a confidence interval that's 95%, we're doing a two-sided confidence interval, then we're going to put 2.5% on each tail. And so what I'm looking there is at the t quantile corresponding to 0.975. Now, one of the things you're going to find different from the book and the table in the back of the book is, and this is by convention that goes way back, if you want the 0.975, you don't look that up in the table, you look up 0.025. Because the way the table is constructed, it's the probability that it's greater than or equal to the value, whereas the cumulative distribution function is the probability it's less than or equal. So R uses the convention that it's less than or equal to a value. So if you want the upper quantile in R, you would put 0.975. However, if you went to the back of the book and looked at the table, you would actually look up 0.0. You would find the t-value corresponding to 0.025 because it gives the upper tail probability. Is that understandable? So again, you can compare what R does. One of the things that's nice here is that you can compare what we do in R with the table in the back of the book or the computations in the book. And for the most part, that works. But there are some differences that do arise, and I'm going to point out those differences when we get to the non-parametric test in just a few minutes. So the upper tail t-value, which corresponds to the 0.975 t quantile with 11 degrees of freedom. Remember, the degrees of freedom is n minus 1, n is 12, so the degrees of freedom will be 11. So this is a small sample t-test. And therefore, assuming that we could use a z-test, which assumes that we know sigma, which only works really if n is large, is probably not reasonable here. In other words, you see that the upper quantile is 2.201, and as I mentioned last time, if you actually went to the normal tables or used R to find the 0.975, you would find out it's 1.96. So it's really the difference between 1.96 and 2.2. It's not a lot, but it could make a difference if your t-value, if you actually computed it and it came out to 2.1 and you were using a normal approximation, you'd say reject, but here we would say fail to reject. So it can make a difference. So at any rate, I'm using R as a calculator here, and I'm computing the lower and upper limits. M, which I computed as a mean, times the t quantile, times S, which I had also previously computed, divided by the square root of n. So I'm computing the upper and lower limits. I should mention here that I had mentioned last time I would get the homework, which I didn't, but I definitely will do that. The first assignment will be on problems in Chapter 8, so you can start working some problems, but either tonight or tomorrow night I will send you a template for 5 or 6 problems from this chapter. Now, what I'm trying to decide is, do I want them R-based? Well, you'll probably use R to compute everything, but some of them, if you look at the problems in the book, some of them don't give the raw data. They give like S, Y bar, and S, and N, and then they say, okay, if you know Y bar, S, and N, you can compute the T, right? You couldn't do a lot else. You couldn't actually say, is it normally distributed, because you need the raw data for that. So one of the things that I like to do is sort of convert things so that most problems have raw data. I know historically people would often give problems where they just gave summaries like Y bar, S, and N, and then they said, okay, from those summaries, compute new summaries like T. And then once you have T, you can do a significant test, but unfortunately you can't do any diagnostics. You can't test whether or not the assumptions hold. And so in real life, you're going to need to do that. It's not enough just to do a t-test and say, oh, okay, this is my conclusion. You need to have some statement of validity about your assumptions. Now, in some cases, you can use the central limit theorem to say, well, if n is large, then y bar is approximately normal, and the t is approximately a z in that case, and therefore everything works out by the central limit theorem. And that's pretty much true for a large n, but there's always some controversy. You know, if you have an extreme outlier, there's still things that can mess you up, you know, unless the sample size is really large. So at any rate, so we can, if you take a look at this, we computed it right where the cursor is, we computed the t. So it's the mean minus the hypothesis. This is a test now, as opposed to a confidence interval. So the t is simply the sample mean minus the hypothesized value over the standard error. And the standard error in this case is s over the square root of n. And you can see that the mean is actually less than 17. So the t value is negative. It's a minus 1.518. And you can see that if it's a two-sided test, we'll take the absolute value and see if it's greater than t quantile corresponding to 0.975. And you see it's false. And we can compute it, and this is actually the way you compute the t-value. The p-value is the probability you get something as extreme or more extreme than the actual computed t that you got. So if I actually put in the computed t, but since it's a two-sided test, I have to say as extreme in either direction. So I'm going to take the absolute value of t, and I'm going to get the probability of that, which is the probability I'm less than or equal. I'm going to subtract that to 1, it gives me the upper tail, and then I double it. If you think about it, if you drew a picture, in this case, the t is negative, so I don't like writing stuff on the board particularly, but I may add some comments about it, but I don't see any. Yeah, there's chalk. Try not to use the board for the people that are not here, but if you draw a bell-shaped curve, and at the lower point, you put the actual computed t, which is a minus 1.518. Okay, so I'm computing the area to the left of that, but I also have to a 1.518 on the upper tail and compute that area. Because I don't know, a priori, that is before I collected the data, I didn't know it was higher than 17 or lower. And so I'm going to actually compute both of these areas, the area less than a minus 1.578 and the area greater than the 1.578. But that's equivalent to taking the absolute value, and then you're getting the probability of less than or equal than this upper limit. Since we're taking the absolute value, you're getting the area to the left of a plus 1.578. So we have to subtract that from 1 to get the upper tail, and then we double it to get the upper and the lower tails. So that's sort of the justification for that computation. Other questions on that? Now, there are various ways we can do this. So we could more directly do that using a built-in function called t-dot test in R. And there you simply specify the variable, miles, and you say mu equals 17. That is the hypothesized value. So if my hypothesis is mu equals mu naught, where mu naught is a specified value, in this case, it's 17. And if you do that, you see that you do get a minus 1.518, like we computed above, and degrees of freedom 11, and the p-value is 0.1573. So you see that we sort of did by hand everything that's directly done. So how are you going to do it in the future? Well, you're probably going to do it this way, which is pretty simple. Notice that you can specify a one-tailed test, either greater than or less than. In other words, I could say it's less than 17, or I could say greater than 17. I could do a one-tailed test. And in that case, I would put all the probability in one tail or the other. So if I were doing a significance level of 0.05, I would use 0.95 as the upper quantile, or minus the t-value corresponding to that for the lower tail, again, with all 5% in the lower tail in that case, if I were doing a one-sided test. Or can, in fact, one of the options is to specify whether it's one side, specify whether or not it is in one direction or the other. If you actually go in and let's go into the help and maybe do this, and let's type in t-test, and you can see the t-test has various arguments, and there's an argument called alternative equals, and it's either two-sided, less, or greater, but by default it's going to be two-sided. And by default, mu is 0. If you don't specify it, you'll be testing the null hypothesis 0. So if you're doing a one-sample test, usually you're not testing at 0. If you do a matched pair test, that's usually what you are going to assume, that it's mu equals 0. Also, notice that by default, if you do a two-sample test, which this isn't, it assumes that the variances are not equal. But I'll come to that point in just a moment when we talk about the two-sample test. So we can do very directly we can say t-dot test and just compute or compute everything for you. But as I said, you have a number of options. Also notice by default that it gives you a confidence interval. So the 95% confidence interval is given, and they give the mean. Now, I'm going to briefly mention, but I need to clarify this particular test. Suppose we have a whole course called Stat 551 on nonparametric statistics. So I'm going to throw in a few things. So what are your assumptions? What What are the assumptions for the one-sample test?
There's no difference between the sample evolution and the mean.
Well, no, we're not assuming a relationship between the sample variance and the mean. That would be true if we were thinking of a Poisson, where the mean and the variance are the same. But in this case, where the assumptions are, the number one assumption is normality. The other is we have independent observations. So can we relax those assumptions? The t-test is called a parametric test because we're assuming normality. We're assuming a particular family of distributions, in this case a normal distribution. It has two parameters that's specified completely, mu and sigma. If you know mu and sigma, you know exactly the normal distribution. What we don't know is whether the data really comes from a normal distribution. That's why I did the probability plot. So based on what we saw at the probability plot, we'd probably say, well, it looks pretty close. And so you're probably not too worried about it. But suppose you do a probability plot and you've got an outlier, or you have extreme skewness, either to the right or to the left. And in that case, you would question the assumption of normality, particularly, and this could become a fairly serious issue if you have a small sample size. Now again, if the sample size is large enough, the central limit theorem will say, well, maybe we can handle it. But again, this is always a question of what do we mean by large? Well, is 40 large? Yeah, usually it is large enough. Usually if sort of 30 is kind of this cutoff, it's more than 30, we say, we're probably okay. The central limit theorem probably kicks in. But if you have a bad outlier, that may not be true. Now, fortunately, we can plot the data, and if we have this outlier that's way out there, we can see it. And so we'll probably handle it. So suppose we relax the assumptions and say, we're not going to assume normality, we're simply going to assume symmetry. Symmetry, a t-distribution is symmetric, but it's not normal. By symmetry, I mean, what we're assuming, let's say, is that the distribution is symmetric about the mean. The normal curve is symmetric about the mean. The mean is in the middle. If you look at the curve in the book, you'll see that it's symmetric. The t-distribution is also symmetric, but it has fatter tails. There's more probability in the tail because there's more variability for the t because S is random. So if you assume symmetry, then we can have what's called, we're not assuming normality, then we have what's called a distribution-free test or a non-parametric test. We're simply assuming symmetry. So the class of families it could be is much larger. It's not only normal, but it could be any other distribution that's symmetric. Now, this may or may not comfort you, and a lot of people fall into the trap of saying, oh, I'm going to do a non-parametric test, and therefore I'm okay. And then they forget that the non-parametric test we're going to talk about at least also has assumptions. They're weaker than normality, but it's still assumption of symmetry. And the problem may be that your data is skewed, or you have an outlier. Well, if you have an outlier skewed, you're not symmetric. It's true, you're not normal, but you're not symmetric. So the non-parametric test is really not going to help you too much in that case. It may be a little bit better, but it's only going to help you in a limited way. So I just want to mention today, and I discovered sort of too late to do anything about it, is that there's a Wilcoxon test called a Wilcoxon sign rank test. And that's one of the first tests you're going to learn in 551. And so the Wilcoxon test says this. If you think about it intuitively, if it's symmetric, then about half the observations should be above the mean, or the median, and half should be, when the mean and the median should be about the same if you have a symmetric distribution. And so about half should be above and half should be below. And so if you're saying, okay, is that true? So what you could do is take miles minus 17, which is a hypothesized value. Those are the different. Those are the deviations from the hypothesized value. You notice some are negative and some are positive. And then we're going to take the absolute value of those, and we're going to rank them. So I actually do those first two steps. I compute D, which is miles minus 17, D for difference. And then I take the rank of the absolute value. And so there's the rank. So can you tell me, just looking at the output, what is the largest, which one is the largest in terms of its rank? It's minus 1.7. Now remember, we're taking the absolute value before we rank. So that's a 1.7. That is the biggest deviation, right? And what is the smallest deviation? 0. It has a rank of 1. Notice it has a rank of 1, whereas the biggest one has a rank of 12. Now, do you notice that there's two 2.5s and two 6.5s? What's happening there? Yeah, they're tied. So let's take you see you have a minus 0.1 and a plus 0.1, and they would occupy ranks 2 and 3. But in what order? Well, when you take absolute value, they're the same. So what we've done is averaged those two and replaced the ranks of 2.5 for each. Now this causes some slight problem in terms of the approximate test we're doing. Likewise at 6 and 7, so we averaged the two 6s and 7s. So the Wilcoxon test, as computed in the book, is different than what's computed here. As computed in the books, it will take like the sum of the positive values. But here's the thing, whereas the book sums everything. Now we reattach the minus and plus signs to the ranks. So the ranks, if you take the ranks and you now put the correct plus and minus sign back on the rank, and then the book would say, add those up, and then average them. And then there's an approximate normal test. Whereas R doesn't quite do it that way. R simply says add up the positive values. Now I claim that that's really the same. If the book, instead of averaging, you don't really have to average, you could just sum the positives and negatives. But I claim that these are actually the same because if you have the numbers 1 to n and sum them, you know what the total sum is. And so, the two tests are equivalent is what I'm trying to say. They look like they're very different, but in fact, they are equivalent. And so I have to sort of decide, since the R approach, if you look at the V test, V is 18, which V is 18, and therefore I said, in this case, correct equals false. By the way, there's a continuity correction, so you may not see exactly the same answers as you might compute by hand. But if V is 18 and the p-value is 0.18, then again we fail to reject the null hypothesis. So I need to put a little bit more work. I have to make some decision, or at least show you what the equivalence is, because if you look at the Wilcox test, it is not quite in correspondence with the book, but they really are equivalent. It's just they don't appear to be equivalent. The way we compute the test statistic is different, but they're equivalent representations. Now, what may be slightly different is the continuity correction. So I need to check this a little bit further to see how this goes. But basically, I just wanted to point out that there is a non-parametric test. You can do T-dot test and Wilcox dot test. Same formula. I mean, the arguments are identical. Well, the arguments I've specified now. Wilcox dot test has some additional, if you look at the help, you see there are some, instead of the T-dot test, the Wilcox test has different, some of the arguments look exactly the same, like x and y. A y would be if you have a two-sample version of this. The alternative is the same. Mu is the same. Paired, you have a paired argument. You have a paired t-test or a paired Wilcoxon test, and so forth. But then there's things like correct equals true, and that's the continuity correction. And the way you compute confidence intervals, the concept of a confidence interval on mu, where you're saying that's sort of a slightly different concept here because we're not assuming a normal distribution, but there is a way you can compute a confidence interval. Now, I wanted to mention that I'm going to put this as a reference. Or did I already do it? I don't know if I did, but if I didn't, I'm going to put this down as a reference. This is called Introductory Statistics with R, and it's by Peter Dalgaard. And it covers a lot of the same topics that we're covering in the book. It has in the first chapters, it has a review of R. But this is a very good book to look at and to complement what we're doing. Now, this book has actually fairly few formulas in it. Typically what it does is it gives an intuitive explanation, and then it gives the R code with essentially no formulas. And it does give some formulas, but not very many. And so you may find that this is an easier introduction than the book we're actually using. And I sort of have, I'm sort of not quite decided on the direction, in other words, to what extent should you use a book like this versus the book we're using, which has a little more detail in it, more information on how you compute things and so forth. This is assuming you've got R and that's it. And of course, when you get out, that may be what you use, or you maybe use jump or SAS or whatever. But so at any rate, this is a nice reference book, particularly on the R part of what we're doing. This book does not hardly do anything on certain topics like experimental design. So I didn't feel like it was quite appropriate for this course, but it is certainly a nice complement. So I'll post this book. You can get an ebook version of this either through I think like on an iPad, either through iBooks or through Kindle. I'm not sure who else has it electronically, but you can get an ebook version. You probably have discovered by now that the ebook versions aren't necessarily a whole lot cheaper than the printed versions, which I've never quite agreed with that philosophy. It's like, well, you don't need a physical bookstore, you don't need printing of it, you don't need shipping, should be less. And it is, but sometimes only a little less, and it's like, okay. So, I will clarify this issue, the differences between the way this Wilcoxon rank test is done in the book and how it's done, which is actually done by hand in the book, and how it's done here using R. So I'll do some clarifications. Now, if you do that, we talked about the match test, and I just want to comment. This was a test that we had where we were comparing, this simple example where we're comparing calculators, and we had each student use each type of calculator. Probably should find another example since you know what a calculator is. It's calculator apps. So, a dedicated calculator was something that got crunched along with many other products with smartphones. At any rate, when we did the paired t-test, we had pairing, we had like an x and a y, and we had pairing. So we're going to take a difference, and once we take the difference, then we're going to test the hypothesis that the mean of the differences, mu, is 0. So in this case, if calculator A, if we're doing A minus B, if A takes longer, calculator A takes longer to use than calculator B, then the differences tend to be positive, and we may reject our hypothesis. So we're actually just doing a one sample t-test again on the differences. So there's really not much new here. So we're doing a one sample t-test. But you notice I just did want to point out to you that once we get the differences, then we still have the same types of issues. Are the differences normally distributed? So again, we can take the differences and we can do a normal probability plot on the differences to see if the assumption of normality holds. And again, we could do a Wilcoxon test, but on the differences. So if we look, there are a couple of ways that we could do this. We could simply take A minus B and get one set of numbers and do it exactly the way we did it with the one sample test, right? But you could, if you've got the actual paired values in two different columns, if you think about in JUMP a data frame where you have two columns, or if it's an Excel spreadsheet, you have one column of the A's and another column of the B's, and you take differences, that becomes a third column. Does that make sense? Then we could take the differences and we could simply do the one sample test on those differences, or we could simply say t-test A comma B, and then we say if paired equals true. If we don't say paired equals true, what happens? It treats it as a two-sample test with A the first sample and B the second sample. So if we give A and B, and they really are paired, then we just have to say paired equals true, because by default it's false. So if we do the paired test, but I just want to point out to you that there's also exactly the same format. In other words, the non-parametric tests in R exactly mimic the parametric t-test. So you have t.test, and you have those arguments, or I could say Wilcoxon.test, and I have A, B, paired equals true. Looks identical. Now this is really the same as what we just talked about with the Wilcoxon test too, because you're taking the differences, you're testing mu equals 0. So we subtract off 0, so we really just have the differences, and we're looking at the plus and minus sign. We rank them, rank the absolute values of those differences, and we look at, again, we attach the plus and minus signs, and so there's nothing different here than what we did in the standard one sample test. So let's take a look at the output. If we look at the matched, pairs, and I actually do this two different ways. In this first way, if you look at the top, I said t.test A minus B with no other arguments, and that simply takes the differences, and we do a t-test, and we see that the t-value is 2.324. There are 12 students doing this, so the degrees of freedom is 12, and the p-value is 0.04. So it's just significant, and we're assuming a two-sided test here. And we get a 97% confidence interval, and notice that it does not include 0, which again would also equivalently say that we have a difference. Notice we're not far from 0 in the lower end, and the fact that 0 is just outside of the interval corresponds to the fact that the p-value is almost, it's barely less than 0.05. So all these things taken together, we reject, but we don't overwhelmingly reject. In other words, the p-value is only a little bit less than 0.05. The 0 is only slightly outside the interval, so we do reject. Now, of course, the difference could be quite real, and it's just that we only have 12, and so we don't have a lot of power to reject with n equals 12. So this is sort of the way you need to be thinking about things. And if you run your own experiment and you've got a small sample size, you are risking failing to reject, or saying you don't reject when in fact you should reject. So if you don't have a large enough sample size, it basically means you have low power, and you may not your research hypothesis is typically the alternative hypothesis. So you may not be saying that I accept the alternative because you have low power. Again, that's something you need to think about when you design an experiment. And in this case, to design an experiment is selecting the sample size. It's a very simple experiment, but we still should have some idea what the power is, because if your sample size is too small, you have low power. But notice there's another way of doing this, and that is we could say t-test AB paired equals true, and if you see, you get exactly the same results. So you could do it either way. And then the Wilcox test, there I'm going to say AB paired equals true, and that's the Wilcox test. And so this is computing the Wilcox statistic V and gives the value. Now I meant to mention previously in the one sample case, if you compared the p-value, and I think this gets them both on, if the t-test has a p-value of 0.157, whereas the Wilcoxon is 0.181. In other words, the p-value is slightly bigger, but they're close. So there's not much difference in the two tests in terms of the p-value. They're both giving you essentially the same answer. And that's partially because we pretty much meet the assumption. Now, let me say this. What do you lose by doing the Wilcoxon test if, in fact, you had normality and didn't need to use the Wilcoxon test? In other words, if you meet the assumption of normality, then why not just always do the Wilcoxon test? Yeah.
Computation time.
If you compute the exact p-value, there is a computation aspect. But the real reason is that the t-test is more powerful. For a given sample size, you have a greater probability of rejecting, if in fact you should reject with the t-test, if you meet the assumption. So you lose a little power with the non-parametric test, around 5% maybe. So in other words, you're losing a little power if you use a non-parametric test. So there is a reason to say that let's do the t-test unless I really feel I need to do it. But again, I want to emphasize that the non-parametric test, in this case the Wilcoxon test, it's not assumption-free. I'm not saying the distribution can be anything. I'm simply saying that we relax the assumption to symmetry. But it's still, we're assuming symmetry. So that's actually still a fairly strong assumption. So just keep that in mind, because a lot of people just are mistakenly, when they're doing the research studies, they're mistakenly assuming that, I don't have normality, my problems are solved, I'll just use, in this case, the Wilcoxon test, or more generally a non-parametric test. That's not the case. Still, you are assuming symmetry. It's not it's a weaker, but not a weak assumption. So if we go down to the matched pair test, let's compare those. Let's look at the p-values. How close are they? Well, you see here, an interesting thing just happened. So our p-value is 0.0403 for the t-test, but what is it for the Wilcoxon sign rank test? It's 0.054. So if you were testing a significance level of 0.05, in the t-test you would reject, in the Wilcoxon test you wouldn't. Now, you could argue, well, they're both close to 0.05 and they're really not very different. But if you were sort of a purist, and most statisticians aren't, but sometimes major professors are, you get different conclusions. If you were strictly testing at a significance level of 0.05, you get a different conclusion here. So I didn't actually plot the differences. We could do that to see if normality is reasonable here. We could do a probability plot to see if normality is reasonable. Again, we have the problem that n equals 12. So now let's go down. Any questions on that? Let's go down to the two-sample test. And so what we're going to test here, this is a two-sample t-test. We have two groups. We're going to test at mu1 equals mu2. That's what we're interested in. We have two populations. They both have a mean, and they both have variances. So you have mu1 for the first group, and it has a variance of sigma 1 squared. And the second group has a mean of mu2, and it has a variance of sigma 2 squared. Now, the classical test, and the way you're usually taught in an intro stat courses is we have certain assumptions. So what are the assumptions here? Can anyone tell me? What are the assumptions of a two-sample test? Two tests. They're usually taught in an intro stat course.
Assumption sample 1 and sample 2 there's no significant.
Well, it's not that it's significant. We're assuming they're normal. We have to assume that sample 1 and sample 2 both come from a normal distribution. And then the stronger assumption that's usually given is that the variances are the same. Sigma 1 squared equals sigma 2 squared. And there's a third assumption that we have independent samples, that each sample is independent of each other, and within a sample, in other words, the N1 observations from the first group are independently sampled from the first population, and the N2 observations are sampled from the second, and they're sampled independently of each other. In other words, what you do in the first sample doesn't affect what happens in the second sample. Those are the assumptions. And I specify those assumptions now. And so we have an example here. And this is this deals with mutations. Basically, if I had a chemical compound and I was concerned about worker safety, and workers are using this chemical compounds, and I want to know, does it cause a genetic mutation, which would not be good for the workers. But you don't want to test workers, do you? We're not going to spray the chemical on the worker and say, well, let's wait 5 years and see if you develop cancer. It turns out that in toxicology, what you might do is look at the effect on certain microorganisms that perhaps are known to genetically mutate, maybe in similar ways that we might mutate. So in other words, a first line of defense may say, okay, well, let's apply this chemical to a microorganism and sort of see if, in fact, there's a mutation in the microorganisms. But certainly we could start there. And so we could do that, and let's suppose we have a control group, and in this case, you may have a petri dish, and you're looking at the number of mutant colonies. So you have colonies on a petri dish, and you want to see how many of those colonies mutate. Now, in practice, of course, you would say, rightly, that I'm counting how many colonies mutate. So I have, what is my outcome? My outcome is 0, 1, 2, 3, 4. In other words, you would say, I'm looking at how many colonies mutate. And you would say, well, that's not going to be normally distributed. I have a count. And if you think of count, what distribution do you think of? There are two in the book we talk about. Well, I maybe talked about 3. I talked about the binomial distribution. I talked about it briefly because I didn't really cover the first 7 chapters very much. But again, the binomial distribution, which we did talk about, the Poisson, which I've mentioned, and then the other is the geometric distribution. So we have 3, and so what do you think the distribution might be? In other words, if I picked one of those 3, is this a binomial experiment? No, I didn't flip a coin and see how many heads I got out of 10 tosses. I could get 0, 1, 2, what's the upper limit? Well, there is probably an upper limit because you only have so many colonies per petri dish. But technically, you have 0, 1, 2. Now, a geometric distribution would be something like this. How many times do I toss a coin before I get my first head? Not that. That's not what we're talking about here. So we're talking about something that might be approximately Poisson. And so you then ask, there are certain things that we know. We know that if we have a Poisson distribution, that in some cases we can transform that random variable into something that is approximately normal. And it turns out that the log transformation often works. That is, we can take the counts and transform them by a log, and a lot of times and there's some theory behind why that's true. We can take the log and we can transform it and get approximate normality. Now this doesn't always work. So if I had zeros, ones, and twos, and in fact I could get a zero, then we have a little bit of a problem. So if you expect counts to be near zero, then in fact, instead of taking the log of x, we'll maybe take the log of x plus 1. So in other words, we'll add 1 to the count so that we never take the log of a 0. So I'm not sure in this case. I think maybe they added 1. No, I don't think they did. I'm not sure. But at any rate, so here's our data, but this data is on a log scale. And this was a log base 10 scale. By the way, the base doesn't matter. In terms of the two-sample t-test, the base of the logarithm, whether you take log base e or log base 10, is not going to matter in terms of computing the t-test. We're talking about a scale difference, so it doesn't matter. So here's our data. So we have the two groups. We don't have an equal sample size here. I did a little summary here. And again, you should look back at the R code. And let's take a look at... Now in R Markdown, tables are a little bit of a pain. But I want you to notice something about that particular code. There's the table in the sort of the middle, starting at line 135. And then if you look at the output right here, it looks pretty good, right? I actually computed the entries in the table using R. And so I wanted to point this out, that the dollar signs for n and the dollar signs indicate LaTeX. That is to say, that dollar sign simply italicized n, which is what we typically do for things, when we have certain statistics, we'll italicize them. So if I have slash bar of y, that's LaTeX saying x bar. That's actually how you put the bar in LaTeX above the y, which means the sample mean. And then S is the sample standard deviation. And then notice under the controls, I have a single tick mark, and I have R. That means this is an R expression. It's an inline R expression. How do you get a block of R code? Well, I have 3 tick marks. And I end it with 3 tick marks. And then I put little braces, and at a minimum I say R, and then you put your R code. But in this case, I have 1 tick mark, I say R, and then I put an R expression. In this case, the R expression is the length of the control. And in that case, that was 7. And below it, you have the length of the treatment. And in that case, that was 8. And then I want the mean of the control and the mean of the treatment. And then I also have that I probably should just change that to SD, but I have the square root of the variance of the control. Believe it or not, there was no function SD not too long ago. That's the way you actually computed it, as the square root of the variance. And we get stuck in that thought pattern. But now there is a function called SD. I guess people complain, why not just do SD? Why should you take the square root of the variance? At any rate, I also round this off to 3 digits. So I'm computing the standard deviation. In the last column, I'm computing the standard deviations and rounding them to 3 digits. And so this gives a quick summary. Gives a nice little table. And notice that the y bar, it is a y bar with the bar above it. And so the backslash bar, and then in braces, in LaTeX, you put the arguments like in braces. So it's a little bit different than R. But we get some summary statistics. And then you're testing the null hypothesis that mu sub c is equal to mu sub t in this case. Well, actually, equal versus it's less than 0. So you're testing that the treated mean has what? More mutants, or more mutations. in the treated mean than the controls. So what your hypothesis is that the chemical causes mutations. That is the alternative hypothesis. And so here we're doing a one-sided test. And so notice that, notice what I've done here is that I'm saying that the ARCA is t-test for the, I have two things, control, CNTL, and comma treated. And so I didn't say pair equals t, so therefore it treats them as a two-sample t-test. If I would have said pair equals t, you would have gotten an error because the links aren't the same. One has link 7, one has link 8. So you would have gotten an error if you put paired equals true. If you put pair equals true, then you would have gotten an error. They're not paired. We have two independent samples. And so the alternative is less, and by default, var equal, the variance is equal, which is an assumption, is false. But I'm going to say, I'm going to do the classical test that everyone does in their interest calculus, that I'm going to say var equals true. So it's going to do the classical t-test. And if you remember what happens, you compute S1 squared, which is the estimate of sigma 1 squared. In other words, you compute the variance for the first group, you compare it for the second group. And then what do you usually do? So I have S1 squared and S2 squared. And if I assume that the variances are equal, sigma 1 squared equals sigma 2 squared equals sigma squared. If they estimate the same thing, I should be able to pool them. And what we do is we do pool them, but we don't just average them. So I have S1 squared and S2 squared. I don't just average them. I'm going to do a weighted average based on the degrees of freedom. And so if you look at the book, they give a formula for that we do a weighted average based on the degrees of freedom. If the sample sizes are the same, so if N1 equals N2, then you do just average them. So if the sample size is the same, you average. But the idea is that if N1 is bigger than N2, then S1 squared has more information as an estimate of sigma squared than S2 squared does, and I give it more weight. That's sort of the idea. And that weighting is done by the degrees of freedom. So that's what we're doing here. And you can look in the book for the formula for what's called pooling the variances. You can look in the book for that formula. To do it by hand isn't too hard, as long as the sample sizes are not big. Notice here that our t-value is minus 0.0885 with 13 degrees of freedom, and a p-value of 0.204. So let's talk about this for a moment. How did I get, if we did a one sample test, the degrees of freedom was equal to n minus 1. Okay, if we did a simple t-test, it was n minus 1. So we lost 1 degree of freedom in the one sample t-test. Now, there are various ways you could explain that. If you compute the sample, if you compute the variance, let's say s squared, when we compute it in the denominator, we divide by n minus 1, not n. And the reason is because of bias. It turns out that s squared is a bias estimator. It means on average, it's not equal to sigma squared. So s squared is what's called a bias estimator. We adjust for the bias by dividing by n minus 1 instead of n. Large sample size, the bias is very small. Small sample size, the bias can be significant. So you do that to adjust the bias. But in this case, we actually have two groups, and we estimate sigma squared for each one, and we divide by n1 minus 1 for the one and n2 minus 1 for the other. So you, in fact, lose 1 degree of freedom for each sample. In this case, there are 2 samples. And so where did I get the degrees of freedom? Since I'm pooling them, it's not just n1 plus n2. What is n1 plus n2? Up there, it gives the n's 7 and 8, right? So n1 plus n2 is 15. But the degrees of freedom is 13. But if I subtract 1 from each of the samples and add them up, it's equal to what? 13. In other words, 7 minus 1 plus 8 minus 1 is 13. And that's where you get the degrees of freedom. you have bias estimates in both cases, and we're adjusting in both cases. We're losing 1 degree of freedom in both cases. And so we lose 2 degrees of freedom altogether, so it's 15 minus 2. So we don't come very close to rejecting. In other words, it appears there's no difference between these two types of calculators. And we can get a confidence interval. We can get a confidence interval on the mean, and there's something to consider here. What is the confidence interval? Well, the thing is, it's a one-tailed confidence interval. I did a one-tailed test, so I'm going to get a one-tailed confidence interval. Since I'm testing that the treated is greater than controlled, then I'm doing a one-sided interval, and I'm going to and therefore I'm going to, instead of giving two numbers, one of those numbers is going to be minus infinity in this case, or if the confidence interval is the other way, it could be plus infinity, depending on which way the interval goes. So in this case, we have a minus infinity up to 0.1714 to get the confidence interval. Now, a lot of times people don't do one-sided confidence intervals, and a lot of times in your intro course you kind of skip this topic. Maybe you don't, I don't know. But at any rate, R can compute not only one-sided tests, but one-sided confidence intervals. And notice that, in fact, the mean of the control is less, but it's not enough less. In other words, the mean of the control is 1.52, and the mean of the treated is 1.68. So it is true that the controls have a lower mutation rate than the treated, but not enough to be significant. So that's our conclusion. Now, if you were doing this test and you're careful, you would also test that the variances are equal. That was one of the assumptions, right? So why not test it U1, sigma 1 squared equals sigma 2 squared? Well, if that's true, then if you look at this formula right here, if the null hypothesis is true, what do you think the ratio of S1 squared to S2 squared should be? It should be close to what? 1. In other words, if the two variances are the same, saying sigma 1 squared equals sigma 2 squared is equivalent to saying what? Sigma 1 squared over sigma 2 squared is equal to 1. Divide both sides by sigma 2 squared. And you'll see that the null hypothesis is really saying sigma 1 squared over sigma 2 squared is equal to 1. So I'm going to use as my test statistic S1 squared, which is the sample estimate of sigma 1 squared. I'm going to use the ratio of the sample variances. And if they're close to 1, I should fail to reject. I conclude that the null looks pretty good. But if the difference is way away from 1, that indicates that either S1 squared is bigger than S2 squared or vice versa. So it indicates that in terms of the parameters, that the population variances differ either one direction or the other. And so it turns out that under the null, and assuming normality, that this is an F-test. Now, unfortunately, there's a little bit of trickiness, particularly if you read the book. The back of the book for the F-test gives the upper tail. Now, if you had a t-test and I gave you the upper tail value, you know the lower tail corresponding to the same alpha because it's symmetry. But the F is not symmetric. It's positively skewed. So you might say, well, if I know the upper tail here, is there a way to find out the lower tail? I can't just say it's negative because the F-test is always positive. It's always positive and it's positively skewed. And so you can't just put a minus sign on the F and say, oh, that's the lower tail. No. But what you can do is take the reciprocal of the F, and that flips around, including the degrees of freedom. And by knowing the upper tail, we can get the lower tail by flipping, and you can sort of mathematically show that. So there's a little trickery here, and I may sort of add to the notes to explain that a little bit, but it is in the book. In the book, you have to do that because that's all you have is the upper tail. Whereas with R, you don't have to do it because I could specify as the argument for the quantile 0.025 or 0.975. I can specify it as the argument. So in R, technically, you don't need to do it. So in R, you can compute the lower quantiles as well as the upper quantiles. So now, this is actually a different example, and perhaps we should have continued on the same example, but suppose, in this case, suppose you have rodents, and you want to know, again, this is counts, you want to know how many parasites these rodents are carrying. In this case, are they rats? Well, and so, in this case, we have let's see. Unfortunately, I don't give quite as much explanation as maybe I should here, but at any rate, we're comparing two different types of rodents, M and R. I guess it's mice and rats, but so we want to know if there's a difference in the number of parasites they kill. So again, here are the parasites, and again, if this is a count, you could consider doing a log transform of this data. So I'm using a new function, and there's various functions we could use. There's a whole group of functions called apply functions. They're mapping type functions, and suppose I want the mean of both groups. And so, in this case, I have a function called tapply. And the first argument, look at our data. If I would have printed out all the values for this, I only printed the first 5 here, but if I would have printed out all of them, I would have had, under the column rodents, I would have had M's and R's. And parasites would have had values going all the way down. So some of the values correspond to M, some of them correspond to R. Again, the two groups. So suppose I want the mean for each group. Now there are a number of ways to do this in R, but one way is to simply do this. Tapply, parasites, that's the random variable we're looking at. And then rodent is a categorical variable, it's a grouping variable. And then I have a function. And I say, I want to map the function mean across the categories. So basically this is saying, for each category of the second argument, I want the mean of the first argument. Now that third argument, mean, I could use other arguments there, like standard deviation or variance. So this that shows you the two means. And you can see that M has a lower parasitic rate than R. And if we in fact look at and I'm just sort of showing you some different things here. This is called a side-by-side box plot. And the parasites tilde rodent, basically that's saying the parasites is modeled as a function of rodent. And what that's going to do for a box plot is actually give you a side-by-side box plot. And bandwidth equals true, it means that the bandwidth is going to be proportional to the variance. So look where R appears to not only have a higher mean, but a higher variance. Now, notice these points up here. What are they? And the point here. Well, these are outliers. In other words, those are outliers. If you had a normal distribution, you shouldn't see that happen very often. So the fact that you have those points appearing means that they're a little more extreme. So it appears that if we have an assumption, and the assumption says the variances are equal, I look at that plot and I say, well, I'm not so sure about that, because on the right it's wider than on the left, And then normality, if you have normality, you shouldn't really have those outliers there. And so it looks like maybe we're violating some of the assumptions. So the box plot is very, very nice for looking at this type of box plot, for looking at the assumptions of the two-sample t-test. In a glance, I can tell maybe I've got a problem. And so if I wanted to compute sigma 1 squared over sigma 2 squared, I have to get the variances. So I could again use that t-apply. And the t-apply, in this case, I'm going to, first of all, we previously got the means. In this case, I'm going to get the variance. The variances are equal, the variance are mapped across rodents, so I get the parasite variances for each group. And I get the sample sizes. So notice that we have a very unbalanced situation. We only have 9 M's and 31 R's, and notice that the variances look quite different. In the one case, the variance for the mice appears to be 13 roughly, and for the rats it appears to be 43. So perhaps there's some concern there. Now, I have computed an F, which I call, look what I call these, the p-var. So the F-test down here is simply the p-var 1 divided by p-var 2. Now notice I'm using a subscript operator. In other words, p-var is a vector of length 2. So p-var, as I computed it above, is a vector of length 2. Notice there are 2 elements, or 2 variances. So if I say p-var and in square brackets I say 1, that's picking out the first element. And so if you look at how I computed F, I'm looking at the first variance divided by the second variance. In other words, that is the F-test I said we should compute. I think I'm running over here, so yeah. So let me just point out a couple things. And we'll come back to this a little bit next time as we finish this up. And I will post an updated version of these notes that have some more materials. And I've got to figure out what I'm going to do about these non-parametric tests. But there is a direct test for variance, var.test. And when I do var.test, it computes the F-test directly and gives p-values and so forth. And notice the p-value is roughly 0.08. So one of the things you might say is, gee, the variances seem really, really different, and yet I don't reject, or at least I don't reject at the 0.5 level. Why is that true? The answer is, and again, you're going to be your false sense of security. This F-test is not particularly powerful for small sample sizes. So we had fairly small, particularly for the one group, we had small sample sizes. So we fail to reject here, although we would reject at the 0.1 level, we just don't reject at the 0.05 level. So, it's kind of in that range where you might reject, or you might think something is wrong. But the problem is that we have low power. And there are some graphical techniques that I haven't really shown you based upon the idea of a normal probability plot. Because if we do a normal probability plot for each groups, the straight line indicates normality, but whether or not the slopes of those lines are the same indicates whether the variance is the same. So there are ways that we can graphically look at these assumptions that maybe are better than just doing a test, which makes you feel good, but then they have low power. And then you say, oh, my assumptions are fine, I can go ahead and do the two-sample t-test, and no, the assumptions may not be fine. Okay, it's just a little bit of a warning. So we'll stop here, and I'll come back and finish up Chapter 8. There's not too much to do here, and then we're going to go into Chapter 9. I'll be giving you the homework assignment so you can start on it, and we're going to start reading in Chapter 9 for next Monday. Any questions?
Is the Kruskal-Wallis the non-parametric version of this, or is that?
Well, a special case of the Kruskal-Wallis. The Kruskal-Wallis is technically the one-way analysis of variance, but a two-sample t-test is a one-way analysis. We can think of it as a one-way analysis of variance with two groups. So yes, you could use a Kruskal-Wallis, but typically there's a specialized test that we can also use, which I actually give I think I put the Wilcoxon test here. I did put in. So we'll talk briefly about that. And later on, we'll look at the Wilcoxon test. Any other questions? Okay.